Welcome to my biopsychology lectures. Today we're going to continue on with the propagation of the action potential. I'll talk a little bit about the myelin sheath and a little bit about local neurons as part of this unit. At the end of this video, I want you to be able to explain the mechanism by which the action potential is propagated down the axon, define saltatory conduction, explain the functions of myelin and how it leads to saltatory conduction, and simply define local neurons and explain their function. Now, when you think about a stimulus, like a hot object here, somehow this information has to get to your central nervous system. If it's a simple reflex, it only needs to make it to your spinal cord. If we're talking about sensation and perception, obviously it needs to make it up to the brain. When the cell body is excited, that doesn't help us if we can't send that message somewhere. And so with some of the neurons, the sensory neurons, for example, we're going to go from the fingertip all the way to a cell body here and into the spinal cord. So that can be a pretty long axon, depending on your size. That's easy, a meter. Okay, so these messages can go quite a ways. Most of the events that we talk about in terms of excitation of neurons and things like that, these are going to be local events that occur primarily in dendrites. Right? But the action potential, that nerve impulse, we have to send a signal a very long way. So in the previous video, we talked about how the action potential is initiated at the axon hillock. Now I'm going to talk about how it gets carried down the axon from your finger into your spinal cord. Now, this is a schematic depiction. It's very simplified, but it should give you a good starting point. You can go back and refer to the text in more detailed discussions maybe after you see this. So first we'll have our axon hillock. You need to remember that initially the axon's going to be at rest. That means we're going to be resting membrane potential. Now, if the axon hillock, the membrane potential exceeds threshold, voltage-gated sodium channels are going to open and it initiates the action potential. Okay? So in this next figure, when that happens, right, the axon hillock reaches threshold, voltage-gated sodium channels rush into the cell. Right, we get our short depolarization of the membrane, and we get the peak of our action potential. You know that soon after that, in this figure, the voltage-gated potassium channels are going to open up. Potassium is going to leave and restore us back to resting membrane potential eventually. All right, but when the sodium ions come in, right, they're carrying positive charge with them, which is why, again, they depolarize the cell. When, let's say I have an ion channel right here, and sodium comes in. When that sodium comes in, it doesn't just stay there, though, right? Remember, things are going to diffuse. So when it comes into the axon, we're actually going to get the leakage all over the place of sodium. Okay, so that sodium is going to come in and it's going to move laterally a little bit. Now think for a second, what happens to the membrane potential here, which is say minus 70, when positive charges accumulate on the inside? That's right, it's going to get depolarized. Okay, so as that charge leaks laterally, it's going to depolarize. Eventually, if we exceed threshold, what happens? Now those voltage-gated sodium channels are going to open. Okay, so they were closed here. Because of that lateral charge, I get depolarization of the membrane. These open up, and now sodium's going to come in. When this sodium comes in, what's it going to do? It's going to leak to the side. What's going to happen to the closed channels here? They're going to open, and sodium's going to come in. That's going to leak to the side, and then you can imagine that happening all the way down the axon. So it's this leakage of sodium leaking laterally that is going to cause the membrane potential to exceed threshold in the axon next to it. Now, at the axon hillock, right, we talked about the leak coming in, depolarizing. I get my action potential here. Remember, resting membrane potential is restored. Okay, so we're back at rest here. Now, when sodium rushes in through the channels here, it's going to leak this way, and it's going to activate sodium channels. We already talked about that. It's also going to leak this way, though. Now, these sodium channels, though, why don't they open? The answer for that is going to be the refractory period. Okay, so these are no longer capable of responding. Even though the membrane potential here may exceed threshold, these don't respond. Okay, they're refractory. And we're not really going to distinguish absolute from relative refractory period for this class. Just know that they're not capable of opening. Okay, so in this situation, charge leaks this way, charge leaks this way. The reason we don't get voltage-gated sodium channels opening and the action potential going back toward the cell body is because these are refractory. Here, though, they open and they propagate down. You know, a couple very important things. In order to get this action potential, right, what do we need? We need the right channels. Okay, so we need sodium channels. We need the potassium channels. Right? And here, both of these, I'm talking about voltage gated. How come there isn't an action potential on the cell body? The answer is simple. They don't have sodium channels or potassium channels. They don't have voltage gated sodium or potassium channels on the cell body. Okay, so wherever there are these voltage gated sodium and potassium channels, we can get an action potential. In a typical neuron for right now, I just want you to think of them being on the axon. Okay? All right. So here is another cartoon illustrating this. Here we've got a stimulus. It's going to result in an action potential. Those voltage-gated sodium channels are going to open up. Sodium's going to rush into the cell, right? It's going to leak to the side. When it leaks to the side, what does it do? It's going to open up channels next to it, okay? When this leaks to the side again, it's going to open channels next to it. Now here, why does it show potassium flowing? Because remember, the action potential is fairly short, just a few milliseconds. Okay, so we'll have sodium opening, and then very quickly we'll have potassium opening. Here's another view. Remember, when we're talking about voltage-gated sodium channels, I want you to think about three basic states. We can have open, we can have closed, or we can have inactivated. Okay, and here this is the same thing as refractory. Okay, so let's just take an arbitrary time point, time 0. And we're looking at the voltage-gated sodium channels. Okay, in here is the inside of the axon. Here's extracellular fluid. Okay, now back here, the action potential is already passed. We're back at rest. Here, we've got our open voltage-gated sodium channels. Sodium is going to come in and again leak laterally. Now, if you look just to the side of that, what's the membrane potential going to be? It's going to be depolarized. These channels, though, aren't open. Okay, they're not open because, again, they're inactive. When this leaks to the side, though, it's going to depolarize this. What's going to happen? These closed ion channels are going to open up. When it opens up, right, that's going to allow the action potential to move on. If I look a millisecond later, those that were open, right, those voltage-gated sodium channels that were open are now inactive. Okay, I want you to make a distinction between open, closed, and inactive. Closed means that nothing is flowing, but they're ready to go. Open obviously means open. Refractory or inactivated means that they are closed and they cannot respond. They can't open at that moment. Okay, so there's a cycle. We're going to go closed, open, inactivated or refractory, then back to closed. Okay, so we're going to have a cycle of these things. What limits how quickly action potentials can occur is how long it takes these inactivated channels to become active again, to become just closed. Now, there's two different types of axons. There's myelinated and unmyelinated axons. Unmyelinated axons are rare. In vertebrate species, you really only see these in the pain fibers. Invertebrates, like insects, cephalopods, octopus, squid, they have unmyelinated axons throughout their bodies. But in mammals like us, almost all our axons are myelinated. When I say much more common, obviously I'm talking about much more common in our body. There's a lot more invertebrates obviously around the world, so most species have unmyelinated axons. But in us, most of the axons are going to be myelinated. These are faster compared to unmyelinated axons. Now, with saltatory conduction, this is a special kind of an illusion in a way. Saltatory means jumping. Okay, so before when I showed you my axon, right, I had voltage gated sodium channels all along the axon. Okay, that's how it would work in an unmyelinated axon. In most of our axons, I left out a detail that I'll get to now. You know about myelin, right? So each myelin bead is going to coat the axon. In between each myelin bead, we're going to have a node of Ranvier. By the way, this is a proper noun, so when you're writing it in a sentence, it should be lowercase node of Ranvier. It's named after a person, it's a proper noun and should be capitalized. All right. Here, in between the beads at the nodes of Ranvier, this is where I have the sodium and potassium channels. And again, I'm referring to the voltage gated. Okay, so underneath the myelin, do I have those? No. I only have them at the nodes of Ranvier. So when we talk about the flow of ions, where can it occur? Only at the node of Ranvier. Okay? So what ends up happening as sodium rushes in, you know that it kind of leaks laterally. Okay? When it comes to the side, it's actually going to increase the concentration of sodium in the area next to it. Right? So if a whole bunch of sodium, and really we're talking about many, many thousands of molecules coming in, they make it really crowded. Those are going to push those ions down this way. And eventually, I'm going to get an increase here. Now, if I get an increase here, what does that mean? What happens to my membrane potential? It's depolarized. If I get enough of those ions there, I'm going to exceed threshold. Voltage-gated sodium channels are going to open up, and sodium's going to come rushing in like you see here. Now, the way I kind of think about this is it's a bus, right? Now, imagine you got a bus, and it's a little bit crowded, not too crowded, and a whole bunch of people come on the front. You've got your nice seat all by yourself in the back, but what happens is people come into the front. Yeah, it starts to get real crowded back there. Okay? So by people coming in the front, by sodium ions flowing in here, it's actually going to increase the concentration of sodium ions here in the back, way far away. Now, what if you're on one of those really, really long buses? Yet this myelin bead is too long. Even though sodium's coming in, it's not going to increase the concentration of people in the back of the bus. Okay, so then we won't exceed threshold. So there's actually a physical limit as to how long a myelin bead can be. If it's too long, you're not going to be able to exceed threshold and your action potential would stop. All right, but that's not the case, obviously. This is sort of the right length. so that when sodium comes in, we get an increase in concentration of sodium here. We still exceed threshold, and our action potential is kind of recharged. Okay. Now, with saltatory conduction, the reason it's called saltatory is the action potential kind of appears to jump from this node to this node to this node. Okay, saltatory means jumping. So this has more to do with the electrical activity and measurement of it. Don't sweat it for this class. But the electrical potential seems to jump node to node to node. Here's another cartoon depicting it. I'm just showing this again in a give you a little bit more of an idea. So again here, the channel's open. Sodium comes in. You can see the concentration here. It's actually going to result in an increased concentration here. So the membrane potential here is going to exceed threshold. When that happens, those open and sodium comes in. Now, saltatory conduction, having myelin, is much faster than unmyelinated. One of the reasons why, let's go back to our bus analogy. Is it faster, you think, for people to come on the front and just kind of push everyone toward the back so the back gets full? Think about how quick that is. Now imagine someone gets on, walks all the way to the back. Another person gets on, walks all the way to the back. Obviously, that's going to be slower, right? So when you're just kind of pushing people to the back, okay, we have less movement, physical distance that each ion needs to cover in order to increase the membrane potential. Okay, so it's much quicker. It actually ends up at the chemical, the physical level, being faster. Yeah, and here again is just another depiction of that. Probably the geekiest race in the history of the world, but we can have an unmyelinated axon and a myelinated axon go in a race. And as you can see, right, sodium comes in, leaks laterally, causes this to open. Sodium comes in, leaks laterally, causes this to open. Sodium comes in, leaks laterally, causes this to open, all the way down. Versus sodium comes in, leaks to the side, causes this to open. Sodium comes in, leaks to the side, causes this to open. So you can see how that's going to be much faster. And people have really looked at the physical basis of this, and everything I've said is not just us thinking about it. It's not just us getting on the city bus. It's actual physical basis to it. So when you do the races, again, you see that the myelinated axon is faster than the unmyelinated. Now, the book talks a little bit about local neurons. I'm just going to mention them in terms of complex behavior. We're really not going to spend much time on these. I just want you to know what they are in case they turn out to be important down the road. Right now, we really don't know too much about these things. There seems to be a class of neurons called local neurons. These have very short axons. These don't have action potentials. They only produce graded potentials. And when I talk about the synapse in the next sets of videos, this will make a little more sense what a graded potential is. These are really difficult to study for many, many reasons. So we don't really have a great idea of what these things do. These are the exception. And there's not very many of them compared to sort of regular, typical neurons that I've been talking about. So in terms of things like action potential, all of that, we're not going to pay much attention to these. We don't know what happens when these things don't work. Now, one thing, if there's no action potentials in these local neurons, what can you tell me about them? You can deduce some characteristics. What causes the action potential? Depolarization of the membrane so that voltage-gated sodium channels open up. As we reset, repolarize, voltage-gated potassium channels are going to open up. So do you think these local neurons have voltage-gated sodium or voltage-gated potassium channels? Turns out you're right, they do not. Good. All right, so that's our kind of whirlwind tour of conduction down the axon. In the next set of videos, I'm going to talk about what happens when that message reaches the terminal and has to be passed on to the next neuron.